In this lesson, we are going to review the applications of integration that we studied this semester. So first, we're going to review area between curves. So sketch and shade the region bounded by negative sine x, cosine x, 0, and 2 pi. And then set up, but don't solve, an integral or integrals that finds the area of this region. So first, negative sine x. All right, so sine will begin at 0. By pi halves will be at -1. By pi will be at 0. 3 pi halves will be at 1, and 2 pi will be at 0. So there is negative sine x. Cosine x will start at 1, cross the x-axis at pi halves, be -1 at pi, be 0 at 3 pi halves, and then back to 1 by 2 pi. So there's the region. Here's the area we need to find. So in general, the way you find the area is you integrate from the left point to the right point and do the top curve minus the bottom curve. But the problem with this particular example is that at this point and at that point, we change which is the top curve and which is the bottom curve. So we're going to need 3 integrals. One from 0 to whatever this point is, one from that point to the next intersection point, and one from the intersection point on to the end. So the first thing we need to do is figure out what those intersection points are. When does negative sine x equal cosine x in 0 to 2 pi? Well, that happens at an angle of 3 pi quarters and an angle of 7 pi quarters. So this first intersection point is 3 pi quarters. The second one is 7 pi quarters. And so the area is given by an integral from 0 to 3 pi quarters. And for that portion, the cosine curve is on top, minus the sine curve, so minus negative makes plus sine x. And then plus the middle region from 3 pi quarters to 7 pi quarters. And for that region, the negative sine x curve is on top and the cosine curve is below. And then from 7 pi quarters to 2 pi, we've flipped it back again, and the cosine curve is on the top, negative sine's on the bottom, so plus sine of x dx. And solving that would get really, really tedious, so mostly I'm just testing if you understand that that needs to be broken up into 3 integrals. So there you go, that would be the final answer. There are possibly other ways to do this correct using symmetry and stuff, but if you feel like that, trying to do that, you totally could, but you don't have to. So you could say have used the fact that there's some symmetry there, and then this region and that region appear to have equal area. Well, this region and this region also have equal area, and you probably could have gotten down to 2 integrals using that. So either way, they're all correct. Sketch the region bounded by the curves y equals x squared and y equals 2x. Set up, but do not solve. I can't make it any more obvious than that, guys. Follow directions. Integrals that represent the volume of the solids when you rotate the region about the following lines. So y equals x squared goes through 0, 0, 1, 1, and 2, 4, as well as negative 1, 1, and negative 2, positive 4. Y equals 2x starts at 0, 0, has a slope of 2, and it's pretty easy from the graph to see the intersection points. Now, first, about the x-axis. Now, I'll set each problem up both ways. So here's the general setup. For the disk washer method, the volume is pi integral from your A to your B, r out squared minus r in squared, d x or y depending. And for the shell method, the volume is given by 2 pi integral and then it's radius times the height times d whatever, depending on what your variable is. So in the case of the x-axis, if we do the disk method first, we slice like this, and as those spin about this axis, they make little washers, little flat circles with holes in them. So the volume will be given by pi integral from, our slices will begin at a value of x equals 0. They will end at a value of x equals 2. The outer radius, distance from axis of rotation to outer curve, that's the 2x. And the inner radius is x squared. Or if you feel like simplifying that slightly, integral 0 to 2, 4x squared minus x to the 4th dx. You don't have to do that last step because I didn't officially ask for it. Now, if we were to use the shell method, we slice parallel to the axis of rotation, whereas the disk is perpendicular. In this case, our slices will look like this, and when they spin, they're going to make little hollow cylinders. And in that case, the volume is 2 pi. Now, the first thing that changes here are the bounds. Because these slices are horizontal, they have a width of delta y, which means we're going to have a dy, and the bounds now need to be y values, so 0 to 4. Now the radius, distance from axis of rotation out to slice, is just y, and the height will be the top curve minus the bottom curve. In this case, the top curve actually is y equals x squared, or x equals root y, whereas the purple curve is going to be y over 2 equals x. Also, you need to have y's here, so we'll have root y minus y over 2, and that's good enough. One way you can check and see that both of your methods are right is you could say evaluate both of these integrals in something like Wolfram Alpha or a calculator, and if they give you the same result, chances are you're probably correct. So if you take that same region and spin it about the y-axis, what changes? All right, so first let's do the disk method. So in this method, you slice perpendicular to your axis of rotation. And notice now that our R out is the black curve and our R in is the purple curve. And our slices have little height delta y, so we begin at a y value of 0 up to a y value of 4. The outer curve is the parabola, and that's x equals root y. So we have root y squared minus the inner curve, which was x equals y over 2. So minus y over 2 squared dy, which you could simplify to 0 to 4 y minus y squared over 4 dy. Now if we do the shell method, we slice parallel to the axis of rotation. So in that case, our slices will look like this. They have little bitty width delta x, so we have 2 pi because they're cylinders, dx, they begin at 0, they end at x equals 2. Now the radius, the distance from axis of rotation out to my slice, is x. And the height, top minus bottom, the top is the line, so 2x minus x squared dx. All right, now let's do some rotation about some lines that are not the x or y axis. So y equals x squared, y equals 2x, and we have the line y equals 6. So here's y equals x squared again. Here's y equals 2x again. And the line we're going to rotate about is the line y equals 6, which is up here. All right, so first let's do the disk method. So we're slicing perpendicular to the axis of rotation. So we have little bitty delta x's, so the volume will be pi integral from x equals 0 to x equals 2. And the trickiest thing are those radii. So r out is the distance from axis of rotation out to outer curve. Now, this little distance here is x squared. The total distance is 6. That r out is 6 minus x squared. R in, similarly, will be 6 minus 2x squared. Now, if we were asked to do the shell method, 2 pi, we slice parallel to the axis of rotation. So our slices now look like this. Teeny little beanie delta y's, which means we are going to use y values. Y of 0 to y of 4 dy. Okay, so next we need to find the radius. It's found in a very similar fashion. The distance up to that little red slice is y. The total distance from x-axis up to blue line is 6. So that radius is 6 minus y. And the height there, the top, or in this case rightmost, most positive, largest x, is the parabola. So x equals root y minus y over 2. What you can think about for these sideways curves is that this number must be bigger. This is a height as in how tall, and the value of x there is larger than the value of x there. So think right minus left versus top minus bottom. In our final example, we'll take that same region and we're going to rotate it around a vertical line instead of a horizontal line. So we're going to spin this about x equals -3. So there's our axis of rotation out there. All right, first let's do the disk. So perpendicular to the axis of rotation, little delta y, so we're going to need to use y values, y value of 0 to a y value of 4. Now, r out, distance from here over to the outer curve. Well, the distance from the purple line to the y-axis is always 3, and from the y-axis to the curve will be an additional x equals root y over. So in that case, my outer radius is 3 plus root y. And then take away the inner, that will be 3 plus y over 2, the quantity squared. Now for the shell method, we slice parallel to the axis of rotation. And the question is what changes here versus the sort of standard. Well, the first thing is we still have this 2 pi. We have the integral goes from 0 to 2. Now the radius will be a bit different. The distance from there to the y-axis is 3 plus whatever distance over we are, which is x. So that will be 3 plus x. And the height, purple curve is the upper curve, parabola is the lower curve. So we'll have 2x minus x squared dx. And I know that shell is a little bit less intuitive, but if you actually had to solve and evaluate this integral, it seems to me that the second one actually is a little bit easier to solve. But if I ask you to set up these problems, you can do them whatever way you want. Now, another thing I want to make sure that you don't don't forget is that not every solid is a solid of revolution. Some things have different cross-sections, and those cross-sections could be different shapes, like squares or equilateral triangles. So we have a solid, and its base is bounded by the region y equals e to the x plus 2, y equals 0, x equals 0, and x equals 2. So first, sketch e to the x plus 2. That is the e to the x curve shifted up 2. Also notice that e to the 0 is 1. So this will go through the point 0, 3, because 1 plus 2 makes 3. And it's going to have a horizontal asymptote here at 2. And its exponential growth increases pretty quickly. All right, now the rest of the bounds are y equals 0, which is the x-axis, x equals 0, which is the y-axis, and x equals 2. So that's the base of our region. If we were, say, to look at it up from the bottom, that's what it looks like. And when we slice it perpendicular to the x-axis, so like this, we get a square. And those squares are smallest on the left because the base is not very big there, and largest on the right. What you've got a picture here are squares coming up out of the page at you. Now the general formula for the volume of a solid is you integrate from an A to a B, and you add up the area of all of your slices. And for the solids of revolution, it just happens that those slices are circles. That's why the formula involves a pi r squared. But in this case, the slices are squares. So my area of a slice is given by a side squared. And this is one of the sides. So one side is given by e to the x plus 2. And our slices begin at a value of 0, they end at a value of 2, and we're adding up all these squares, so e to the x plus 2 squared. And then it's pretty much as basic integration. Expand, e to the x plus 2 multiplied by e to the x plus 2 is e to the 2x plus 4 e to the x plus 4. Notice that when you multiply e to the x times e to the x, those exponents add. So e to the 2x plus 4 e to the x plus 4. Anti-differentiate, 1/2 e to the 2x plus 4 e to the x plus 4x. Evaluated from 0 to 2. So that will be 1/2 e to the 4th plus 4e squared plus 8 minus, plugging in 0 does not give you 0 for each term, minus 1/2 plus 4 plus 0. So we have 1/2 e to the 4th plus 4 e to the 2nd. So that will be 4 minus 1/2, so 4 minus 1/2 will be 7/2. But the point there is not every cross-section is a circle. So in this question, you actually have to use cylindrical shells. So use the method of cylindrical shells to find the volume, obtain when you rotate the region y equals cosine of x squared, y equals 0, x equals 0, and x equals root pi halves about the y-axis. So this vertical line right there was supposed to tell you that that was x equals root pi over 2. It does appear to be awfully close to 1.25, but this is the exact value. All right, so we're slicing this way, spinning about the y-axis. So 2 pi integral from x equals 0 to root pi over 2. The distance out to a slice is x. The height of a slice is given by cosine of x squared. And that's the setup. From there, it's just doing a substitution. I'm going to let u equal x squared, and du is 2x dx. So half du equals x dx. And if x is 0, well then u is 0. And if x is root pi over 2, u is root pi over 2 squared, or pi over 2. So this is 2 pi times a half, integral 0 to pi halves, cosine of u. The half and 2 cancel, giving us pi. Antiderivative of cosine is sine. So that's pi times sine of pi over 2, which is 1, minus cosine of pi over sine of 0, which is 0, giving us pi. So the volume obtained when you spin that region about the y-axis is pi. Now another application we had was arc length. So the arc length formula that we derived was that the length is given by an integral from a to b, root 1 plus y prime squared dx. And these problems are often quite tricky. There's sort of a limited number for which they work out well, and this happens to be one of them. So y prime, or dy dx, is 12, so 4 times 3 halves x to the 1 half, which is 6 square root x. And our length will be given by an integral from 0 to 1, root 1 plus 6 root x squared dx. So that's 1 plus 36x dx. Now if we do a substitution, let's let u equal 1 plus 36x. du is 36 dx. When x is 0, u is 1. When x is 1, u is 37. So this is an integral from 1 to 37. 1/36 u to the 1 half. So that's 1/36 u to the 3 halves times 2/3, evaluated from 1 to 37. So the 2 and 36 can cancel, making 1/18 times 3 makes 1/54, times 37 to the 3 halves minus 1. That's good enough. We're not testing your arithmetic, we're testing your calculus. In this unit, we also found formulas for the surface area of solids of revolution. So in general, if you take and spin something, so if you spin about the x-axis, the surface area will be given by the formula 2 pi y. That tells you the circumference of your slice times the length, which is this thing we're going to call ds. And we'll explain what that is in a moment. If you go about the y-axis, now it's 2 pi x, because the radius of your slice is now an x, times ds, which is the length of the slice. And that ds comes from the arc length formula. It's 1 plus either y prime squared if you want to use x's in your equation, or you could do 1 plus x prime squared if you want to use y's in your equation. Just depends on the context. So we're rotating 2x squared between 0 and 1, so a parabola, about the x-axis. So this part gets spun. So the surface area can be given by an integral. Let's just use x's. X is 0 to x is 1. 2 pi y is equal to 2x squared. Square root, the ds equation will be 1 plus f prime of x is 4x. So 4x, the quantity squared, dx. Or that's 4 pi integral 0 to 1 x squared times the square root of 1 plus 16x squared dx. You're not asked to solve that, just set it up. And for the y-axis, we can actually also use x's. We just leave that x alone, kind of like we do when we do cylindrical shells. So in this case, the surface area will be 2 pi x integral from 0 to 1, and the same ds, 1 plus 16x squared. You could also have found this by plugging in what x was equal to by, say, taking 2x squared equals y, and solving for x. You could say x squared equals y over 2, and therefore x is root y over 2. And you could have said, okay, 2 pi integral root y over 2, and then inside that root you're going to have to put in what the derivative of this is, ugh. I say ugh. If you want to try that, fine, go for it, but I think that it's easier to just know that you can just use x. And one more thing about the alternative way is you would have to change what the bounds were. They'd have to be y values now, so they would have to go from 0 to 2 instead of 0 to 1. All right, consider the region bounded by the curves, and I probably should have just said curve, sine x, and I'm assuming the lines y equals 0, x equals 0, and then between 0 and pi halves. So sine at pi halves will be up at 1, and by pi be back down to 0. So we're looking for the centroid of that region. And it appears like it should probably be someplace about here-ish. Like the x value should be a little bit closer to pi over 2 because there's more stuff near pi over 2, and the y value should be closer to 0 than to 1 because there's more stuff down here. So the first thing if we're finding centroids is we need to find the area. So the area is equal to an integral from 0 to pi halves sine x dx, so easy as can be. Antiderivative of sine is negative cosine, and that will be negative 0 plus 1, or 1. So the area of that region is 1. To find the centroid, as in the sort of balancing point, the formula for x bar is 1 over the area times the integral from a to b x f of x minus g of x, and the center y coordinate is 1 over 2a integral a to b f of x squared minus g of x squared dx. And in this case, our g of x function is actually 0. So our x bar will be 1 integral from 0 to pi over 2 x times sine of x. And for this, you're going to recognize you have to use integration by parts. So to do that, you let u equal x, du is dx, dv is sine x dx, and v is minus cosine x. So x bar will equal uv, so negative x cosine x, evaluated from 0 to pi halves, plus the integral from 0 to pi halves of cosine x. All right, so x bar will equal, so plugging in pi over 2, we're going to get negative pi over 2 times 0 plus 0 times 1. So that first term actually is just 0. The antiderivative of cosine is sine. And so our x bar is going to be 1. And since pi over 2 is approximately 1.5, that seems like a plausible value. Now, y bar is going to be given by a half integral from a to b, so 0 to pi over 2 sine squared x. And to evaluate this, you're going to have to use your half angle identities. So that will be 1/2 times 1/2, or a quarter, 0 to pi halves, 1 minus cosine of 2x, or 1/4 times x minus a half sine of 2x, evaluated from 0 to pi over 2. So that's 1/4 times pi over 2 minus 0. And the last term is all 0, so this is just pi over 8. So our center of mass is the point 1 pi/8. The next tricky thing we had was work. So here's a question pretty similar to the one that was given on your exam. You have a 1,500-pound elevator that's suspended by a 2,000-foot cable that weighs 12 pounds per foot. How much work do you need to do to raise the elevator from the basement to the 5th floor, which is a distance of 50 feet? So here's the picture. You have your big 1,500-pound elevator. Up here, this total distance is 200. I'm going to call that x sub I, be the distance we have to move a chunk. So in general, the work is equal to the force times the distance traveled. Now, in this case, the work will be the work for the first 50 feet plus the elevator itself plus the rest of the cable that also moves 50 feet. So the first 50 feet is the part that's trickiest because in that first 50 feet, every single piece moves a different distance. So the work to move a slice is the force on that slice times the distance that that slice moves. And I think these slices have little with delta x. The force on the slice, well, this weighs 12 pounds per foot, and I have a slice that's delta x feet long, and it moves a distance of x sub I. Notice how an x sub I is measured in feet. And notice how this ends up giving us the units 12 x sub I delta x, and we are actually in foot-pounds. And so to add those all up, we integrate from 0 to 50, and the function we integrate is just 12x dx. Now the elevator component's actually pretty easy. It has a weight of 1,500 pounds. It moves a distance of 50 feet. And the rest of the cable is actually also pretty easy. What we have to figure out is how much does the rest of the cable weigh. So the rest of cable, there are how many feet? There are 150 feet times 12 pounds per foot. Well, that gives us 1,800 pounds of cable. So plus the 1,800 times 50. This second part, actually when we did this in class, we set up as an integral, but this is a bit easier. And now if we anti-differentiate, we get 6x squared from 0 to 50 plus 75,000 plus 90,000. And this first component ends up being 15,000. And this is 180,000 foot-pounds. Next, we're going to just do a quick average value example. So find the average value of this function. And be very careful that you actually notice the entire function, because if you miss part of it, you might not be able to actually integrate what you're looking at. So the general formula for the average value of a function is 1 over b minus a, integral a to b of the function. What this does is it sort of adds up all the y values of that function and kind of divides by how many there are. It finds the average y value. So 1 over pi over 2 minus 0 times the integral from 0 to pi halves e to the cosine t sine t dt. That's the same thing as 2 over pi times the integral. Now to evaluate this integral, we need to use substitution. Let u equal cosine t. du is negative sine t dt. If t is 0, u is 1. And if t is pi halves, u is equal to 0. So 1 to 0, negative e to the u du. I'm going to flip the bounds and negate the integral, which makes this positive again. And the antiderivative of e to the u is e to the u. And so our final answer is 2 over pi times e minus 1. So just be careful that you actually read the whole function. And the final topic we discussed was fluid pressure and force. So we have a tank that's the shape of a parabola 4x squared. So go through the point 0, 0, and 1, 4. It's a very steep parabola, sort of a U-shaped tank. And we want to find the force on one side of the tank, so that side of the tank. And the general formula for the force was the weight density, W, so W is the weight density of whatever liquid you have, times the integral from some C to some D, times the depth, which they called h of y, and times the length of a slice. All right, so first of all, the weight density we are told is 9,800 newtons per cubic meter. And if we have our parabola graphed this way, our y values begin at 0, they end at 4. Now, the depth. So here's the part that's a bit tricky. If I have a y value of 1, I'm actually at a depth of 3 underwater. So here, notice that if this is your y value, the depth is actually 4 minus the y value. And then the second thing, and notice also that that's going to be measured in meters. The length of a slice, that's how wide these slices is, because the force is approximately constant on those little bitty slices. Well, we know that y is equal to 4x squared. So y over 4 is x squared, and therefore x is plus or minus root y over 2. So the distance from the y-axis over is one of those positive root y's over 2's. We have 2 times root y over 2. And that's also in meters times the dy, which is the thickness, which is also officially counted in meters. So simplify this slightly. We get 9,800 integral 0 to 4 minus y times root y. And if you look at the labels, this integral will have a value that's cubic meters multiplied by the newtons per cubic meter, and that's going to give us an answer that's in newtons in the end.